Hi, in today's video, we'll have a look at the central limit theorem, which is one of the most foundational theorems in all of statistics. So, what does the central limit theorem tell us? Well, it tells us that the distribution of the sample mean x bar will approximate a normal distribution as the sample size becomes large, even if the distribution of x is not normal. Okay, so let's think about what that truly means. Okay, so the sample mean x bar. So you take a sample and you calculate the mean for that one sample. But now, if you were to do that many, many times with different samples, and you were to calculate all of the x bars and plot, let's say in a histogram, all of the x bars, what you would get for x bar is a normal distribution when the sample size becomes large. Okay, and what is extremely powerful about the central limit theorem is that this is true even if the distribution of x is not normal. And it's actually a very, very general theorem. So if we think about the assumptions that are needed for the central limit theorem to work, they're actually quite broad. So one of the main assumptions is that all of the observations xi in the sample are drawn independently from the same distribution, right? So that's a relatively general assumption. And the second one is that the mean and the variance of x is finite. And so that's more of a technical assumption, which in most cases will be satisfied. There are a few distributions where that is not true, but for all the distributions that we're going to be interested in, you don't need to worry about that at all. So another way in which we can express this is as follows. For sufficiently large sample size, the following approximation holds. X bar is distributed, so that tilde is a way of expressing that it's distributed approximately as a normal distribution with mean mu and variance sigma squared divided by n. Remember that for a normal distribution, the only two parameters that we need in order to fully define the normal distribution is the mean mu, in this case, and the variance, in this case, sigma squared divided by n. Okay? And mu is the population mean of x, and sigma squared is the variance of x. Now, let's try to wrap our head around this notion of central limit theorem and what it means, because there's a lot of misunderstanding around this concept. So let's consider a 10-sided die where each side has the same probability of coming up. Okay, so the data is uniformly distributed, and if I draw a histogram of basically the different outcomes and the probability of each outcome coming out, we can see that there's a 10% probability of getting a 1, 10% probability of getting a 2, all the way to 10% probability of getting a 10. Okay, so that's our x variable. So now, let's say we roll the die 3 times and calculate the average outcome. And we repeat this previous step 10,000 times. Now, this is the distribution that we get, okay? So remember, what I'm calculating is the average from my sample of 3. So for example, in my sample 1, I might get 1, 6, 2. In my sample 2, I might get 3, 9, 7, all the way to my sample 10,000, where I might get 1, 4, and 8. Okay, so that's basically how you do it. And so if I take the first sample, that means my x bar is equal to 9 divided by 3. So the 9 is because we get 6 plus 2 plus 1 divided by 3. So I get 3. So my x bar is equal to 3. I would do that for every single sample. And then I would look at the distribution that I get for all of those results. So what do we see? Well, now a temptation would be to say, oh, well, it looks normal because there's broadly this bell-shaped curve that we see. But one thing that we notice very clearly is that there are some gaps basically between the different columns. Okay, so when the sample size is so small, there are a lot of values that are completely impossible to reach. And here, if we were to compare to a normal distribution with the same mean and the same variance, well, we can see that this would be the corresponding normal distribution. Okay, so when I look the normal distribution with the same mean and variance compared to the green distribution, we can see that they're very, very different. Okay, even though you have this general bell shape. So in this case, we would say that the distribution of the mean of 3 die rolls is not normal. Okay, but what happens if we roll the die 10 times and do exactly the same process? Okay, but now our sample size is 10. So we calculate the average outcome for every single sample of 10 die rolls, and we plot all the different averages, okay? And we get the distribution of the mean of 10 die rolls. Now, we can see that there are peaks at different values, which are clearly above what a normal distribution with the same mean and variance would be, but we can already see that it looks a lot more normal. Okay, it's not fully there, but for example, at the tails, it's working pretty well. And around the center, that's where we have like, you know, sometimes there's values for which the probability is going to be too low, values for which the probability is going to be too high. But overall, it starts looking a little bit more like a normal distribution, but with a sample size of 10, we are still too far from a large sample size to actually apply the normal distribution theorem or the central limit theorem. Now, let's say we roll the die 20 times and calculate the average outcome. And once again, we repeat the previous step 10,000 times. And now we can see that the distribution of the mean of 20 die rolls is a lot closer to a normal distribution. It's not perfect. We still have like a few places where we can see that there are dips. And sometimes it's a little bit higher than the prediction, but it's working pretty well. Okay. And if we go to 50 times, it's even better. And if we go to 100 times, now it's starting to look like a great approximation, okay? So even when we think about large sample sizes, it doesn't have to be too large. Here, if we think about, we only have 100 observations, which is not large when we think about the different types of data sets that we may come across. Very often you'll have data sets that have much larger sample sizes than 100. And remember, we also had original data that was extremely non-normal. Okay, we started with a variable that was uniformly distributed. And even with just a sample size of 100, we already have a distribution of the mean that is very close to our normal distribution. And if we go to 1,000 times, now it's really very close to a normal distribution. Okay, so the central limit theorem tells us that the sample mean will be distributed normally with a mean of mu and a variance of sigma squared divided by n, when n gets very large, or that this works well as an approximation. But in practice, obviously, we only observe one sample, not 10,000 samples, like in the toy example that we looked at. But thanks to the central limit theorem, we know that the sample mean that we observe in our one sample will come from a distribution that is approximately normal, right? So that will tell us basically something about the distribution that the sample mean we observe is coming from. And that will help us when we do hypothesis testing. So that's it for today's video. I look forward to seeing you in the next one.